A ball of mass 79 grams drops vertically onto the ground and bounces off at an angle of theta equals 35 degrees as shown in figure C4. The initial and final speed of the ball hitting the ground is 42 meters per second, and the collision takes a time of 13 milliseconds. Find the impulse on the eye, impulse I on the ball. Find the average force acting on the ball. Okay, so first step is we'll redraw the diagram again. So a ball comes in vertically, drops vertically, and then goes off at an angle. (35°). Our mass is 79 grams. It's not in kilogram meters in seconds, so we'll switch to our standard units, kilogram meter in seconds, by multiplying by 10 to the minus 3, multiplying by kilo. Kilos 10 to the 3, 10 to the minus 3 would cancel each other, so it's 79 times 10 to the minus 3 kilograms. And we're told that the velocity that it bounces off the ground is 42 meters per second. Standard units, so that's good. So our impulse, so we're going to use I hat and j hats. So we'll put the impulse is equal to the total momentum after, let's call it final, minus the total momentum of the system, initial. So the total momentum final, so we know that this is VO. We're told that this is the angle theta. So here's our triangle that we have to calculate. So we want the x component, which is this way, so the final component this way. So the ratio of this side to the hypotenuse is sine. So this is mVO sine of theta I hat. So this is the component, this component along the x-axis over the hypotenuse VO plus MO, the component this way, right? The component this way. The final momentum velocity is mVO cosine of theta j hat. So this is the final momentum minus the initial momentum is going to be mVO going straight down. Minus. So here is our initial I component. Here is our j component. I'll put a double line. Okay, so we're going to rearrange these in terms of mVO sine theta I plus mVO. So cosine minus minus is a plus, so m cosine, and we have cosine of theta plus 1 j hat is the impulse. So our calculation for our impulse would be, I'll put numbers in here, the last step, which is 79 times 10 to the minus 3 times a velocity of 42 meters per second times sine of 35 degrees. 79, it's not scientific numbers, but we can enter these in the calculator. Cosine of 35 degrees plus 1 j hat. So we'll bring out our calculator. So 79 exponent to the 3 minus multiplied by 42 multiplied by 35 sine gives me, to two significant digits, it's 1.9 times 10 to the 0, so it's just actually 1.9 newtons. So let me get an eraser. To two significant digits, because all the numbers are two significant digits. Plus, let's do the j component, 79 exponent to the 3 minus multiplied by 42 multiplied by parentheses 35 cosine plus 1 close parentheses equals .0, and the impulse is in standard units of, so it's in Momentum units, which is kilogram meters per second. But remember, a kilogram per meter per second is also Newton seconds, depending on how you look at it. So you could write either kilogram per meter per second or Newtons seconds. Okay, so the first part, we have to calculate the impulse. So I is equal to 1.9 newtons this way, followed by 6 newtons up. So the force is acting on a diagonal. Okay, so the next step is that we need to calculate the time delta t. So the interaction, the force is impulse times delta t. Sorry, impulse divided by delta t. So delta t times so the force is equal to the impulse divided by delta t. So in this case, we have 13 milliseconds. I'll actually use the original equation, which is over here, which is MOVO sine of theta I hat plus MOVO times cosine of theta plus 1 j hat, all divisible by delta t to get the average force. So we put numbers in the final equation. Is this on the screen? Hopefully you guys can see this. So the mass is 79 times 10 to the minus 3. The velocity of, so 13 milliseconds. I put delta t down. I didn't put delta t down. Milliseconds, which is 13 times 10 to the minus 3 seconds. So standard units. VO is, I have it right here, 42 meters per second, right? It's 42, yeah. 42 sine of 35 degrees, all divisible by 13 times 10 to the minus 3 plus 10 to the minus 3 times 42 times cosine of 35 degrees plus 1, all divisible by 13 times 10 to the minus 3 j hat. So I'm going to write the final answer because it's on the screen. I'll put the rest of the equations right here. So F is equal to, it is 1.9 divided by 13, but I'm going to use the original equation because there might be a precision error that I dropped in the original equation. So I'm going to use the new equation and recalculate. Should be about the same answer, but 79 exponent to the 3 minus multiplied by 42 multiplied by 35 sine divided by 13 exponent to the 3 minus. So I have 146. So 146 corresponds to 1.5 times 10 squared I hat. 146, yeah. And 79 exponent to the 3 minus multiplied by 42 multiplied by parentheses 35 cosine plus 1 close parentheses divided by 13 exponent to the 3 minus 464, which is 4.6 10 squared j hat. Force is in newtons, so our impulse is, where's our impulse? Oh, here we go. So this is our impulse. So it's 1.9 I hat plus 6.0 j hat. Kilogram meters per second or Newton seconds. So that's our impulse. So there's an impulse applied on the ball as the ground hitting the ball and making it bounce at an angle of 35 degrees. So remember, the ground hits the ball and the ball hits the ground are basically the same thing. It's just an action-reaction set of forces. Then the force that the ground applies to the ball is 1.5 10 squared I hat times 4.6 times 10 squared j hat newtons. So the applied force is somewhere at an angle.